Assalamu alaikum wa rahmatullahi wa barakatuh. Dear students, in this lecture, inshallah, you will learn what is stationarity. This is, dear students, one of the most important topic we have in statistical analysis, especially in regression analysis. In our previous sessions, if you remember, we have discussed some assumptions related to the model, such as the CLRM assumptions and the Gauss-Markov assumptions. And the purpose behind those assumptions was simply clear, just to make sure whether the model is blue or not, whether the ordinary least square method we are using for the purpose of estimating the parameters is simply based linear and unbiased method or not, right? So now today's lecture, dear students, we are talking about stationarity. Keep in mind, dear students, stationarity is not part of those assumptions. Simply you can say stationarity is not part of the CLRM and the Gauss-Markov assumptions. It's just talking about the property of the time series data. It means if you have a time series data at hand and the purpose is to run regression analysis, so alongside those assumptions we have, such as the CLRM assumptions, right? The classical linear regression model assumptions we have covered, such as the assumptions of fixed x value, there should be no endogeneity, there should be no autocorrelations, no heteroscedasticity, no multicollinearity, right? And there are some other assumptions. Alongside those assumptions, dear students, we should check for the stationarity. And this stationarity has nothing to do with the model, whether it's blue or not. This is just talking about the property of the time series data, dear students, right? It means if the stationarity is missing, still the model can be blue, but the output which is given, dear students, are the relationship between variables that is just spurious, or you can say not realistic. The model is just simply overfitted in that situation, right? Okay, so if it is really important, then what is stationarity, dear students? Stationarity refers to a property of time series where its statistical characteristics do not change over time. This means if you have a time series data, dear students, at hand and the purpose is to check the relationship between variables, then keep in mind each time series variables you have, there are some certain statistical characteristic in that time series. They should not change over time, right? They should just remain constant over time. So these situations are data sets we have, and we call it the time series data set. Why? Because all the variables we have, the data on these variables, they are collected across different points in time we have. Such as the GDP, we have the data points we have here, they are collected in the year 2001, 2002, 2003, and similarly, the government expenditure data set is just collected across these points in time. So if you have a data set in this format, simply this is a time series data set, right? Okay, now what are those statistical properties and characteristics in the time series data variable that should remain constant? And if they are not constant, then you can say there is non-stationarity, or the model is, or you can say the data set is just missing the stationarity. Okay, those characteristics are properties. They are simply, you can say, the mean value, the variance, the covariance, and skewness, kurtosis, and probabilities. If these statistical properties, dear students, they remain constant across different points in time or over the time, dear students, simply you can say the time series data, or this variable of the time series data, dear students, is simply stationary, right? Okay, what do we really mean by this? It means if the mean value you're just checking in this time frame, or you're just checking in this time frame, or just checking in this time period, dear students, the mean value is just constant. It does not change. Similarly, this is the variance, which is just showing the fluctuation, or you can see the spread around the central value distance in this time frame or in this time frame or whatever time frame you're just choosing the distance. So you can say the variance is simply constant. Similarly, the covariance is constant. And what is the covariance? The autocovariance of these variables distance. Or you can simply say when you're just checking the lag dependence of these two variables distance, or these two values, right? Or these two values. You're checking whether the GDP in this point is just dependent on the previous point or not. Or you can say in this time period, the GDP is just dependent on this time period or not. In this situation, dear students, we are checking for covariance. So the covariance is also constant with respect to time, dear students. Okay, similarly, there is no skewness. The skewness is constant, the kurtosis is constant, the probability. These are just statistical properties, dear students. When they are constant across these points in time, dear students, in your dash sets or your dash series, the time series variable, then, dear students, simply you can say there is stationarity. This is the concept of stationarity, dear students. Hopefully, it's clear. Okay. In stationarity response, we have two types of stationarity. One is strict stationarity and one is the weak stationarity. When you are checking for all of these statistical properties in your data set response, and then it means you are checking for the strict stationarity. But when you are only concerned about these three, which is mean, variance, and covariance, it means you are just checking for weak stationarity. And keep in mind, dear students, for all statisticians in research, generally the weak stationarity is acceptable. Why? Because it's really hard just to check the stationarity for all of these statistical characteristics, right? So now when we are talking about the stationarity, it means we are just talking about these three characteristics, right? Technically, you can say, if these three characteristics, mean, right? Number one, you can say the mean value. If the mean value distance, the expected value of xt, the time series, right, that is mu, this is constant, right? If you're just checking, keep in mind you should just check the stationarity for each variable here. So any time series you are just choosing here. So the expected value of the x time series, that is, should be constant. This is the first requirement. Number two, the variance. Technically, you can show the variance of the xt. This value should be constant. The third condition is the covariance. The covariance of the xt distance and xt minus 1, that should depend on the lag value and not on the time. This is really important. Okay, once again, if in each variable you have the mean value is constant, right? The expected value of the xt is constant. The variance, this is simply constant, or you can see the volatility or the spread around the central values, that is simply constant, right? Or the covariance, you're just checking the dependence of xt on the xt minus 1. If this dependence, or you can say this relationship, is just because of the lag value and not because of the actual time, right, then it means the covariance is, or you can see the time series data is just simply stationary. So if these three conditions, they are just simply met, then you can say the weak stationarity is there, right? Okay, now what happens, dear students, if these three conditions, they are not met, or if your data sets or your time series data set is just missing these three important statistical properties for any of the variable, dear students? Okay. Okay, look here, dear students. What is stationarity? This is what we have discussed. The types of stationarity we have covered, dear students. And the statistical properties, this technically I have just explained, dear students. Now I'm just talking about the issues. What happens if these issues, or you can say if these properties, they are not there, right? Number one, first you should learn how the graph look like for the mean value. If we have, this is the t, dear students, and here we have xt. If the values, they are just across different point in times, they are just looking like this, right? In the average value, dear students, that is just a straight line here. So this is the example of a stationary data resistance where the mean value is constant. For each time period resistance, you can just observe that the mean value is simply constant. You can say this is the mean value, the average line here, resistance, okay? So if the mean value of the actual points, we have the xt, different points we have, that is just simply constant, then you can say the first condition is simply met. Or you can say the mean value of the xt, expected t value, is just constant, right? Okay, what happens, dear students, if the mean value is not constant? Then the graph is simply just looking like this. Look, dear students, this is a graph. Here we have t, here we have xt, right? Then the data is just looking like this. Look the behavior. The trend is just different. Okay, look, now the average line is just here, dear students. Now the difference between these two graphs, dear students, here the average line, this is just straight but same, right? But here, dear students, the average line is just different. Why? Because for each value of the x, the average value is just lower. It's just trending upward. You can say the average value here is just smaller, and that is just getting bigger and bigger and bigger in this way, right? But in this graph, dear students, across given points here, we have the time period, dear students, the average line is just constant. That does not change. You can say that's same. Okay, this is the issue of the stationary distance. If the average line is just not constant distance, then the coefficients or the estimates we have the distance, that is just not computed in correct way. That is again a problem we have the distance, right? Why? Because the estimates we have the coefficients that should give you one value. So in these situations, if the trend is just different, or you can say the value is just going upward in the situations, or the average value is just going upward. In that situation, it's really difficult for the model just to give you the average value. Even though the model is blue, but the coefficient estimate or the beta value is not just okay because of the time series data distance. Okay. Okay. Also, if you have a model distance like this, we have t and we have xt. But in this model distance, we have the same average value. This is the first assumption is met, but the variance is different distance. By the variance, we mean in the beginning the variance is just small, but this is just getting bigger. It is just bigger. So look, so this is a situation distance where the variance is just different. This is just different like this. So look, this is just getting bigger and bigger. Although the first condition is met, you can say the mean value is just straight and simply same, right? But the variance, which is the black line, this is just getting bigger and bigger and bigger. So in this situation, as you can see, the second property is missing here, in a sense. Okay, this is the perfect situation where you can observe both of them, the mean value and the variance, both of them, they are just constant. The third property, which is covariance. In the covariance, the graph is just looking like this. So look here. Here we have t, and here we have xt. And this is a straight line. It means we have the variance is also same, but the variance is just, look dear students. Now you can observe dear students, the variance is same, but the covariance here is just different, right? And here is just moderate. Here you have, look, the covariance, the value of the covariance here and here. So this is just different across different points in time. So in this time period, the covariance distance, in this time period, the covariance, in this time period, the covariance. Although the variance is same, it means that's just not fluctuating. The spread around the central point distance, that is just same. But the covariance, you can say the dependence of the two values, the xt over xt minus 1 is here. This is just one way, here is another way, and here this is just different. You can say this is. So in this situation, you can say the covariance property is missing. And this is the situation where in this example, you can say the mean value, right? The mean value and also the variance and the covariance, all of them, they are simply constant. And if you have a data sets with these properties looking a graph like this, then you can say the data is simply stationary distance. Okay. Okay, now inshallah you learn how to check for stationarity. Okay, we have different methods. You can use this augmented Dickey-Fuller test method. You can use the Phillips parent test method, KP-assist test method, ERS. But simply for the sake of simplicity reasons, we are just using one method, which is augmented Dickey-Fuller test. Inshallah, you learn how to resolve the issue of non-stationarity if there is any non-stationarity in any variable distance. Okay. Okay, so you should have your Stata file open. Click on the file, and here click on import file from the Excel spreadsheet, and here we have a special file by the name of stationarity. Okay, in this file, students, GDP are dependent variable, government expenditure and exports investment, they are independent variable. This is just not relevant. I'm dropping it. Okay, the first point is you should learn that if your data set is time series data set, so you should tell this data that what is your time variable. So you should type TSSET and the time variable is year. So now the time variable is set and just run the regression. Run regression. This is a dependent variable and I'll check all our independent variable and press enter. Okay, we have not taken the dependent variable. Okay. GDP, government expenditures, exports, investment, and press enter. Now this is the output response. Once again, as I've explained many times, response, this output is not considered unless we are sure about some assumptions and also now about the stationarity. We are just checking for the stationarity. This output, or you can say the relationship, is spurious in case there is non-stationarity. So we should make sure we have stationarity or the data is just non-stationary. Okay. So the if value response, this is the showing the model is simply significant overall, and the number of independent variables we have two which are they are significant, and the investment this is not significant, right? Okay, now before considering this output response, we are checking for the stationarity. For stationarity, we have augmented Dickey-Fuller test. So you should type D Fuller, right? And then what is a variable? Each and every variable response should be checked for stationarity. So we are just first checking stationarity of the GDP, and just comma, and then you should type leg because we are interested to check the one leg and press enter. Okay, this is the augmented Dickey-Fuller test result. In this output, just look at the p-value. The p-value is less than 0.005. So what is the null hypothesis response? The null hypothesis, the data is non-stationary, and the alternative hypothesis, the data is stationary. Okay, when the null hypothesis is having a unit root means the data is not stationary. And alternative hypothesis here is that there is stationarity. So if the p-value is less than 0.05, it means the data is simply stationary. Just the variable of GDP is stationary. Now we are checking for another variable. So you should just type the same variable, D Fuller, and take the government expenditure as a second variable, and type leg 1. Okay. Okay. The p-value is also less than 0.05. It means the data sets are, you can see the variables of the government expenditure is simply stationary, right? And D Fuller, and take the third variable, which is export, and leg 1. Okay, the export is also the p-value is less than 0.05, so you can say that export is stationary. This time series variable is simply stationary. Now we are checking for investment. So D Fuller and investment. Okay, the value of investment response, this is just greater than p-value 0.05. So this simply means the variable, the investment variable, is non-stationary. So here is a problem. We have just checked for the stationarity of all variables. One among them, this is investment, which is non-stationary. Okay, what do we have to do for this non-stationary variable? We have some solution response, right? Okay, we have different method you can just use response. So you can use the first difference method for solution for correcting the issue of non-stationarity. You can use the log transformation method, the detrending method, or you can just use the ADF method with trend options. So we have many methods, and the functions I have, you can just use this Terra for that. The commands are also here just given. So for the sake of simplicity, we are just using the first difference method, right? So what is the first difference method? You just generate the first difference of the variable you have. For example, our variable, a variable which is non-stationary, that is investment. So just generate the first difference, D investment equal sign and D dot investment. This is amount response, right? This is just generating the first difference. So one variable created response, this is the first difference, right? Now check the stationarity. So D Fuller, and take this variable, which is the first difference variable, and type leg 1. Okay, now the p-value response just decreased significantly. In our previous p-value that was greater than the p0.05 value response, and now it is less than 0.05. It means now the issue is simply resolved. So we have the investment variable, which is just okay for analysis. Why? Because now it's stationary. Simply it is just stationary. Okay, You have learned, dear students, if the variable is not stationary, then have to make it stationary. We have simply used the first difference method. You can use the log transformation method just to transform the value, take the log of the value. This is just the function, I have to use this. Okay, or you can just use the detrending method to remove the deterministic trend method. This is just the function, the formula you can use. Or you just using the ADF with trend options. This is another, the modified version of the defuller, right? So if this method is just not working, try for the second one, and the third one, and the fourth one. But we are just using the first one, and the first method just simply work. And we found out that our variable now, dear students, is simply stationary, and it's okay for analysis. So after that, dear students, once your variable is stationary, just simply run the regression and take the dependent variable and all independent variable. But keep in mind, instead of investment, use the transform. This one, which is the first difference of the investment resistance, right? Press enter. Now this is the output resistance which can be considered. You can just use it. You can say the relationship is not spurious, right? Alongside other assumption resistance, now the issue of the non-stationarity also resolved. Hopefully, dear students, you have just learned the idea of the stationarity, dear students, okay? And also you have learned how to remove the issue of non-stationarity if there is in the data set, dear students. Assalamu alaikum warahmatullahi wabarakatuh.